All right, so now we can talk about inverse trigonometric functions. Inverse functions are a little bit harder to kind of see and everything, so we kind of got to think about them in different ways. And we're going to start to see different ways of solving and everything. We've already seen one little example before, but now we're going to dig into the deeper level of things on what we can do with them. So the first one we're going to talk about is our inverse sine function. So if we're given our sine graph here of y equals sine of x, our sine function is not directly invertible because of the fact that if we sit here and we look at it, we can see that it keeps repeating, but we have places where it has zeros, where it is could possibly be undefined and everything. So we need to come up with a way that when we take an inverse, it has to be unique. So we can't have it being this repetition and everything in order for it to work. So since it has to be a unique, just like we learned in a previous math course, that all inverses are unique, we need to restrict some things. So instead of taking the entire sine function, we're going to take one little sliver of it. We're basically going to cut it from negative pi over 2 to pi over 2 here. And that's going to give us this piece right here. So y equals sine of x only between negative pi over 2 and positive pi over 2. So we have this little s cubic function style, however you want to look at it and everything. So by restricting this domain, we end up with only a little piece of it. So we're going to be able to see what we can do with that in just a second here. Likewise, we can do the same exact thing for cosine, but instead of going from negative pi over 2 to pi over 2, that's not going to do us any good because our y values would repeat. And we know for inverses, your x and y cannot repeat. We want to restrict this from 0 to pi to give us a smaller thing to work with there. So if we just looked at the cosine function between 0 and pi, that would bring us to this nice little function here. So in a lot of cases, we're seeing that sine and cosine can go together and do stuff, but we need to make sure that we are seeing how we can do things individually. For tangent, it's already in like a nicer form for us because we already can define it between negative pi over 2 and positive pi over 2 by the way that the period runs. Period on the previous two was 2 pi, the period on tangent's only pi, and we're kind of looking to reduce it down to a pi. So by doing this, we create just a standard. We're going to actually end up using the entire tangent for one full period here. So it's going to be slightly different for sine and cosine just because we're having to cut the graphs there versus tangent, we do not. So if we looked at the graphs of our inverses based off of those that we already found. So notice that for inverse sine of x, that we have a domain from -1 to 1 and a range from negative pi over 2 to pi over 2. So if you kind of remember back to pre-calculus when we talked about inverses, we switched the x and y. So the range of the original function was between -1 and 1, and the domain was between negative pi over 2 and pi over 2 for sine. When we go to its inverse, we just switch them. Same exact thing for our cosine of our inverse cosine. Just the only difference is its range is from 0 to pi instead of negative pi over 2 to pi over 2. For inverse tangent of x, our vertical asymptotes become horizontal asymptotes, hence the range from negative pi over 2 to pi over 2 not inclusive anymore. And our domain, since we can keep going and never touch them, it'll be negative infinity to infinity. So here's kind of giving us a summary of what we already know here. So for our trig function, y equals sine of x, in terms of inverse pieces, for the restricted domain, we're going to be between negative pi over 2 and pi over 2 inclusive. Whereas the entire domain of sine of x for one period is 0 to 2 pi. Cosine of x is very similar, except for our restricted domain is going to be 0 to pi inclusive. And its original one period was over 0 to 2 pi. So they both, sine and cosine, both have a period of 2 pi on their original and just a period of pi on the restricted function. For tangent of x, its restricted domain is parentheses negative pi over 2 to pi over 2, which happens to be the exact same thing as the one period of the original function. So these domain restrictions for the original become the ranges for inverse sine, inverse cosine, and inverse tangent respectively here. So we've got some values to look at here. So we want to be able to figure out all four of these given what we already know. So the easiest way to do that is hopefully we've memorized our unit circle by now. So if we were looking at where, one way to kind of look at these, I call this my cheating simplified method here. If I said that x equals inverse sine of negative root 3 over 2, then that would mean that sine of x is equal to negative root 3 over 2. So the question is, where is this true at? Well, negative root 3 over 2 is going to be where? What if we look at our unit circle here? That inverse sine is equal to negative root 3 over 2. So if we did that, we could see that the inverse sine of x equal to negative root 3 over 2 would give us a negative pi over 6 value here. If we were to do inverse tangent of root 3, so where would inverse tangent of root 3 be? So that's going to be pi over 3. For inverse cosine of 1/2, so where does cosine equal 1/2? That's going to give us pi over 3 as our answer. So a lot of this can be found by looking at our unit circle. So inverse tangent of negative 1 is going to be negative pi over 4. So in a lot of these cases, there's more than one answer. So why are we only picking certain values? Well, that's going to bring us to some other stuff we're going to talk about in just a second with some summary rules on why we're only picking one of these. So for this one, it says use a calculator to find the value of the following expression in radians rounded to 2 decimal places. So if we were to bring up our calculator and we were to do inverse sine of √5 divided by 7, so if I just brought up my calculator, it might give me this right here. But how does that translate to here? And I do this for a reason. It gives us a hint here in radians. This value here is in degrees. So keep in mind that our calculator needs to be in radians when we find this answer out. And that's how we get the 0.33. Actually, we get 0.325136653. Well, since it says round to 2 decimal places, we get 0.33 as our answer. So always make sure that's going to be one of the biggest things now is determining whether our calculator needs to be in radians or needs to be in degrees. Because if we're in the wrong one, 0.33 is a lot different than 18.63. So the next thing we can talk about is our inverse properties. So one of the main things that we're having to make sure of is that when we are looking at stuff, that we're making sure that we're in the right intervals. So a minute ago, when I actually took the sign of sine inverse to get stuff, I really didn't say what I was doing. All I did was just say sine of x equals negative √3/2. Well, this right here kind of gives us a more definite procedure that we have to sit here and consider. So when we do that, what we get is that sine of sine inverse of x is equal to x for all x inside the interval -1 to 1. If we're outside of that, it doesn't work. Sine inverse of sine of x is equal to x for every x inside of -π/2 to +π/2. For cosine, cosine of cosine inverse of x is equal to x for x every x in the interval -1 to 1 again. Cosine inverse of cosine of x is equal to x for every x in the interval 0 to pi. And the tangent of tan inverse of x is equal to x for every real number x. And tan inverse of tangent of x is equal to x for every x in the interval -π/2 to +π/2. So far when we've been doing things, we've just been taking it at face value. What is the answer? And we're done. Now we have to make sure that we're following every single one of these rules. So your unit circle is going to come into play, as well as these properties right here. So we got 3 cases to consider here. Sine inverse of sine of pi/10. So by our rules, sine inverse of sine, our value x must be in the interval -π/2 to +π/2. Well, in this case, pi/10 is in between that because basically inside the interval -π/2 to pi/2, this would be, in terms of tenths, -5 pi/10 to +5 pi/10. Pi/10 is inside of that interval, so these kind of just cancel out, leaving us with pi/10. So for the next one, cosine inverse of cosine of -π/4. So cosine inverse of cosine, it needs to be in the interval between 0 and pi. Well, cosine of -π/4, -π/4 is not inside that interval. However, cosine is an even function. So we could make this cosine inverse of cosine of pi over 4, since it's an even function. And therefore now pi over 4 is inside of this interval. So therefore we just get pi over 4. So for our last one here, tangent inverse of tangent of 3 pi over 5. So where is 3 pi over 5? Because it says that we need to be between negative pi over 2 and pi over 2. So in terms of fifths, well, we could go to tenths to make this negative 5 pi over 10 and 5 pi over 10. But this is actually 6 pi over 10. So this value is actually not inside of this interval. But if we actually think about what is 6 pi over 10 or 3 pi over 10, so if we were to draw this out, 3 pi over 5 would put me somewhere like right here. So that angle goes outside of the interval because I can only include the first and fourth quadrant. However, if I think about this line, I could subtract pi, so subtract 5 from that. And I'm going to get to the same value because tangent has the same value in the second quadrant and in the fourth quadrant, as well as the first and third quadrants have the same. So tangent of 3 pi over 5 is the same thing as tan inverse of tangent of minus 2 pi over 5, because minus 2 pi over 5 falls inside of my interval. They have the same value, which is all we're looking for. Therefore, the answer is minus 2 pi over 5. So for inverse properties and functions, this section really digs deep into that. And there's a lot of stuff we have to kind of think more intuitively about than just being able to take it at face value for what we're seeing. We got to see, is there a way could we manipulate it and get to the same value? If so, it may still be possible. So continuing on with these, the tangent of tangent inverse is of x is equal to x for all real numbers x by our properties. Therefore, tan of tan inverse of 14 just gives me that 14. Now, for sine of sine inverse of x, we must be on the interval negative 1 to 1, but pi is 3.14. No way we can rewrite that, so therefore that is not possible. So now we kind of think about this in a different way. Sine inverse of negative 1/6. So basically think about this as y equals sine inverse of negative 1/6. So therefore sine of y is equal to negative 1/6. We can then draw our triangle. So sine of y is negative 1/6. My last side is root 35. So then we really have secant of y. Well, secant of y is just 1 over cosine of y. But cosine of y is root 35/6. But I need 1 over that. So we end up with 6 over root 35, which is 6 root 35 over 35, which is our answer here. So we have to be kind of thinking about this intuitively in order to be able to do this. Sometimes we may be able to draw a triangle off of it. A lot of times when we have mixed functions here. So secant and sine inverse, or cosine and sine inverse, or sine and cosine inverse, stuff like that. We might need to think about the drawing a triangle if possible. So we're told use a right triangle to write an expression assuming x is positive and the inverse trig function is defined. So again, y equals sine inverse of 3x. So therefore sine of y is equal to 3x. So if this is my y, sine of y, so that's really 3x over 1. So 3x and 1. By using x squared plus y squared equals z squared, we would end up with 3x all squared plus y squared equals 1 squared. Y squared equals 1 minus 9x squared. Y equals the square root of 1 minus 9x squared. And that's how we got to here. So in this case, we would have cosine of y. So cosine of y is square root of 1 minus 9x squared. So that's how we get to our answer here. So same exact theory here. If we let y equal tangent inverse of x over 5, tangent of y is equal to x over 5. So we have our x over 5, and then we have x squared plus 5 squared equals z squared. So x squared plus 25 equals z squared. Z equals the square root of x squared plus 25. So then you have sine of y is really what we're dealing with way up here, not down there. So sine of y is equal to x over the square root of x squared plus 25, which is what we have here as our answer. So properties of inverses are pretty detailed and technical that we have to make sure we're worrying about. We have to check to make sure each one of our values is correct each and every time. So just make sure that we are learning those and applying them correctly and everything. Keep in mind that sometimes your sine and cosine and tangent might be the same in a different quadrant that you might be able to use a different value for. And that could help us simplify things.